Okay, so suppose we have some vector v here in orange, and suppose we also have some plane, pi. And this is the plane spanned by the vectors a and b. These are the direction vectors for the plane. And we want to find the projection of the vector onto the plane. So this vector here, this is the projection of the vector v onto the plane pi. So suppose we want to find this, and first of all, suppose we want to figure out what this is before we find it. That would probably be a good idea. So what is the projection of the vector v onto the plane pi? Well, if we recall, when we had a vector, so let's say this is, I'll just call it v again. We're going to abuse notation here, as they say. Suppose we want to project v onto the vector u. And more specifically, or more precisely, we want to project it onto the span of u, so onto the line spanned by u, all the scalar multiples of u. Well, what was that? What was that projection? Well, that was what we get if we connect v, the tip of v, to u by this line, this line segment, which is perpendicular to u. So we connect the tip of v to u at a right angle, and then we take this bit, this scalar multiple, this bit here of u. And this is sometimes called the component of v in the u direction. It's kind of a way of measuring how much in the u direction v goes. And why is that? It's because if we look at the projection of v onto u, so this here is the projection of v onto u, and then we have this vector here as well. We can see that v is actually equal to the projection of u onto, or of v onto u, plus, if we call this w, plus this w vector here. And this is what's called an orthogonal decomposition of the vector u, or of the vector v. So for any subspace, this is the span of u that is a subspace of, in this case, R2, but it could also be R3 or Rn. For any subspace and any vector, we can always write that vector as the sum of a vector which is in the subspace. And actually, I should write this part here. The projection of v onto u, that's a scalar multiple of u, so it's in the span of u. It's in that subspace, and we can always write any vector v as the sum of a vector in that subspace for whatever the subspace is, plus an orthogonal vector. So plus a vector w, which is orthogonal to that subspace, which is in what's called the orthogonal complement of that subspace. So that's getting a little bit ahead of us of ourselves here. So this thing here that we're doing with this projection of v onto the plane pi is just sort of a generalization of that. It's sort of a next step, because a plane is also a subspace. A plane through the origin is a subspace. A line through the origin is a subspace. And sort of at the end of this, we'll think about, like, what if this plane was translated, and we'll see that the way that you find the projection is just by finding the projection at the origin and then translating the projection to wherever the plane is. But we're sort of tacitly assuming, as we always do, that all of these vectors here are at the origin. This is the origin here, and then we can move them around afterwards. But we're doing all these calculations at the origin. So the idea is that lines and planes through the origin are subspaces, and when we project v onto this plane through the origin, which is spanned by a and b, what we're actually doing is finding an orthogonal decomposition. We're finding the sort of component of v that is in the plane, right? We're finding this vector, the projection of v onto the plane pi, which if we then add to it this vector here, this vector there, this is like our w, the orthogonal bit. Well, that is perpendicular to the plane. That is orthogonal to the plane. It makes a right angle with every vector in the plane. So you can take like this point here and then connect it to any vector in the plane, or any other point in the plane, and you're going to get a right angle there. So it's orthogonal to the plane. and we have by writing v as the projection of v onto pi plus this w vector, which is orthogonal to the plane. We have decomposed v into its component in that subspace, and then the component which is in the orthogonal complement of the subspace. So this is kind of just the next step. So it's a very similar thing that we're doing to finding projections, orthogonal projections onto planes. We're decomposing the vector. So now let's see how to actually do it. And the reason, one of the reasons that we're tarrying over this and thinking so much about the orthogonality is that the way that we're going to do this is by looking at an orthogonal vector, a vector which we know is going to be orthogonal to the plane, and that is over here, already drawn in, this normal vector n, which is the normal vector to the plane. What we are going to do in order to find w is we are actually going to project v onto the normal vector, or onto the span, the line spanned by the normal vector n to the plane. So we're going to find that normal vector, and then we are going to project v onto n. So this is our w vector. This is actually the projection of v onto the normal vector. And so again, so this is kind of saying, right, because the normal vector is orthogonal to the plane, right, when we look at the projection of v onto n, we're looking at sort of the component of v in the direction of the span, the subspace spanned by this vector. Because again, the span goes in both directions forever, and so we're sort of looking at how much of v goes in the direction of this thing which is orthogonal to the plane, and that is what gives us the w, and so then. And that allows us to find projection of v onto the plane, because we know from our orthogonal decomposition theorem, although I shouldn't call it a theorem because I'm not proving it here, but it is absolutely a theorem. The projection of v, for now it's just sort of intuitive and we're going to take this for granted, but the projection of v onto pi, right, plus w is equal to v. As I'm thinking about this, I'm thinking I should probably make a video where I prove this. Now that I've mentioned it, I kind of have to. Okay, for later. So we know that the projection of v onto pi plus that vector w plus this vector w is equal to v. What does that mean? That means that if I can find w, well, w is the projection of v onto the normal vector. Oh, and by the way, how do I find the normal vector? Well, I can take the cross product of a and b, or I can take b cross a. It doesn't matter, because as we saw in the video for projections onto lines, the projection onto a line, right, or onto a vector is actually the projection onto the span of the vector, and the span of a cross b is the same as the span of b cross a, right? Because a cross b will be like that. Actually, that will be b cross a. Being a liar, we have to keep in mind our right-hand rule. That's b cross a, and then this will be a cross b. So and the span of those vectors, because they have opposite directions, is going to be the same. The span of a vector and then the negative of that vector is going to be the same always. So yes, the idea is that we can just compute the cross product of those, and then that gives us this w vector here, which is the projection of v onto n. We know how to project onto vectors, onto their spans, so we can compute n as either a cross b or b cross a. Then we can project v onto it to get this w vector, and then that allows us to isolate because we also know v. We're assuming that allows us to isolate the projection of v onto the plane pi. We know that the projection of v onto the plane pi is going to be equal to v minus w. It's going to be v minus w, or v minus the projection of v onto the normal vector n, where again n is going to be a cross b or b cross a. It does not matter which. And that gives us the projection of v onto the plane pi. So that's terrific. That's terrific that we have the projection of the vector v onto the plane pi. But suppose now we want to go one more step, and we want to reflect this vector v across the plane. This is actually what allows us to do that. So if I want to reflect v, I'll call this v like prime, across the plane. Well, what do? And we've seen this in other contexts, reflecting across lines is very much the same principle, right? I want to find that vector w. And I should use a different color that is going to stand out. I've used too many colors. Maybe this thing. This looks like, yeah, there we go. Okay. So I'm now looking at actually the negative of w. So going the opposite way, right? So that is negative w. And if I want to look at it from a different perspective, I can say that this is because the vector connecting point A to point B is going to be B minus A, right? Or let's use P and Q because we haven't used we've already used A and B here. So if this is the vector connecting going from P to Q, this is going to be the same as the vector Q minus P. And that's just from our definition of vector subtraction. So I can think of this W, which goes from the tip of V to the tip of the projection of V onto pi. I can think of this as the projection of V onto the plane pi minus V, right? Because that connects. It goes from V to the projection of V onto pi. That is the same vector. And then I can just, and so to reflect it through the plane, I just add that again. I just keep going. I go the exact same distance at the exact same angle, and that reflects across. So, across the plane. So what have I done here? I've taken one of these projections of V, onto pi minus V, and then I take another one, right? So I'm going to add another projection of V onto pi minus V. But what have I added these vectors to? Well, I started at the tip of V here, right? So, and I'm using this color too much. Let me switch again. I started at the tip of V. So if this was the origin, I first went up by V, right? So that was a V, and then I added this projection of V onto pi minus V, and that got down here, and then I added it again, and that got down here, and then if I'm at that point and I connect that the origin to that point in that order, right? So from the origin to here, that gives me the reflection of that vector, across that plane. So adding all those things up, and I'll try to do it in the same color, will give me V plus, that got me to the first part, V plus projection of V onto pi minus V, and then I added another one of those, projection of V onto pi minus V, and this, well, one of these V's is going to cancel, right? This will cancel with that, and we will end up with 2 times the projection of V onto pi minus V. So exactly the same thing as reflecting a vector across a line, right? It's just, we're just doing this with the projection onto the plane. So as long as we know how to, if we know how to reflect a vector across a line, and we know how to find the projection of a vector onto a plane, just the way that we found a projection of a vector onto a line, then we can similarly reflect the vector across the plane.